Hi everyone, in this video we are going to be solving exponential equations. We will also be solving logarithmic equations. That will be the next topic, but for now we're just going to solve exponentials. To be able to solve exponentials, you do need to know a few key properties. So the first property I'm going to give you is an exponential equation property. So property of exponential equations. So this property is kind of obvious, but it definitely needs to be said. So what it says is for b greater than 0 and b not equal to 1, if b to the x equals b to the y, then x has to equal y. It's pretty straightforward here, right? If you have two powers with the same base that are equal, right here, then the two exponents must be equal, right? So if I have b to the x equal to b to the y, that x and that y has to be the same. So for example, just to illustrate it, if I have 2 to the third equals 2 to some power, well, that power is going to have to be 3 because these two things are equal, and the only way they could be equal is if the exponent is exactly the same because they have the same base. So that's the first property we will have to use when we're solving. The next properties have to deal with the fact that logs and exponents are inverses of each other. So these now are the inverse properties of exponents and logs. Okay, so the first property says that if you have log base a of a to the x, that has to equal x. Let's just fix that so it looks more like I wrote log properly. And I don't know why I changed to gray, but it's fine. All right, so I'm going to explain why this is true. So I'm going to explain it using some properties of logs, right? I'm going to start with this side. We know that we have that power property of log, so I could bring the x to the front. So it'll be x times log base a of a. And then I could actually figure out what log base a of a is. So this is asking the question, a to what power equals a? Well, that's only going to happen for 1. So this equals 1. So I have x times 1, which is just x. So I just showed you why this property is true. Okay, the next property says if you have a to the log base a of x, that equals x. So again, this is inverting itself. And the way that I'm going to show you that this one is true is using numbers because I believe it's easier to understand. So let's say we had 10 to the log base 10 of 1,000. So the claim is that this should equal 1,000, right? If we base it off of this property, those x's are now 1,000, the base is 10. So let's think about what we have here. This exponent up here, I could evaluate, that's log base 10 of 1,000, so that's saying 10 to what power equals 1,000? Well, that's 3. So that means that instead of log base 10 of 1,000, or the common log, I could write it as 10 to the third, because log base 10 of 1,000 is 3. And then 10 to the third does equal 1,000. So I just showed you why this property is true. These two properties are going to be very, very useful when we're solving both exponential and log equations. So we really need to know these two properties. Okay, so you're going to want to add those to your notes as well as the first property that I showed you. Now I'm actually going to start solving, and I am going to have to use all these properties. So here's our first example. Okay. We are going to solve 4 to the 3x equals 8 to the x plus 1. Okay, so remember that we have this property that if the bases are exactly the same, that the exponents have to be the same. Okay, now as it is for this one, the bases are not exactly the same, but I could rewrite it so that they are the same. Okay, I know that both of these are powers of 2, so I could rewrite 4 as 2 squared, and then I'll still have this 3x, and then I could write 8 as 2 to the third, and I still have the x plus 1. So what I did here was I rewrote the 4 and the 8 to have the same base. And now I'm just going to clean it up a little. So I'm going to rewrite it as one single exponent instead of right now how I have 2 exponents here and 2 exponents here. So I'm going to use my power to a power property of exponents. So this first one is going to become 2 to the 6x because I multiply these exponents. And then the second one's going to become 2 to the 3x plus 3 because again I'm multiplying these exponents, so that does have to get distributed. Okay, so now I see that I have my property. 2 to some power equals 2 to some power. So those two powers have to be equal. So that means I know that 6x has to equal 3x plus 3. And now I solve this, so I'm going to subtract 3x from both sides. I get 3x equals 3, divide by 3, and I get x equals 1. And now I always check my answer, because when you're solving, you might as well, right? You know whether or not you got it right by substituting back into the original equation for x. So I'm going to have 4 to the 3 times 1 equals 8 to the 1 plus 1, right? So I replaced both x's with 1. So this side I have 4 to the third. This side I have 8 squared. 4 to the third, that's 4 times 4 times 4, which is 64. 8 squared is 64. 8 times 8, and that works. So x equals 1 is my solution. Okay, let's do another one. Okay, so in this example, we're going to solve 2x equals 2 to the x equals 7. Excuse me. All right, so my first attempt usually is to see if I could rewrite the equation to have the same base on both sides, but like it's not so easy to do here with the 7, so I wouldn't recommend that approach. Instead, because I want to solve for x, I'm going to have to use the inverse of an exponential. Okay, so that inverse is going to be using a log. I'm going to use the inverse property that said log base a of a to the x equals x. All right, so that means I'm going to have to take a log of both sides, but I'm going to have to take a log that makes sense. So I'm going to have to take a log that matches what I have. So in my equation, I have 2 to the x. So I'm going to want to take the log with base 2, because that's the only way that it's going to invert itself. These have to match to get x as a result. So that means I'm going to take the log base 2 of 2 to the x. The only way I could do that to the left-hand side is if I also do it to the right-hand side. Whatever I do to one side of the equation, I have to do to the other. So I'm going to also take the log base 2 of 7. All right, what happens on this left-hand side is I just get x, right? I'm using this property over here. And what happens on the right-hand side is I have log base 2 of 7. Now, some of you have those really fancy calculators that you could just plug in what log base 2 of 7 is, which is totally fine. You're done. You isolated x. You could just go ahead and do that. But some of us have calculators that don't have that feature, like me. So I am going to use what's called the change of base that you have in your notes already, right? This is a property I already gave you. So for change of base, we're going to rewrite log base 2 of 7 as log base 10 of 7 over log base 10 of 2. And that's what I'm going to type into my calculator. And when I do that, I get 2.807. And as always, I check my answer. So I would plug this into my original equation here. And I have 2 to the 2.807. Type that into my calculator. And because I did some rounding, it may be a little bit off. So let us see exactly what I get here. Yeah, I get like 6.9982. That's because I rounded this value. It wasn't exact, but I know I get 7. Okay, I'm going to do one more example, just one that is just a little bit more complicated algebraically.